So the first thing we did last class, we introduced the ordinary differential equations, their types, ordinary or partial. We talked about the boundary value problem, initial value problem, the difference between the two, etc. So starting from today until the end of the term, we will be talking about how to solve those ordinary differential equations. So today we will talk about the Euler method and the modified Euler method. Okay, and we will have some examples about how to implement both of them, and then we will have more techniques as we move on. Okay, so the first of all, the first question that we need to ask ourselves: what is the format that we should put our equations in before we proceed in the solution? So we need to reformat or reconfigure the first order differential equation that we have in certain format before we start the solution. So generally speaking, this is the format that we want to have our equation with. The derivative part in one side, and since this is first order differential equation, so I will have only one term, only one derivative term, and this is since this is ordinary differential equation, there will be no other derivative terms with respect to other independent variable. This is not a partial differential equation. So we will keep this with a coefficient of 1, and then everything else will be on this side. Okay, so this is the format. So for example, if I have this differential equation with the initial condition, we said that we will need, this is initial value problem, so we will need an initial condition, and for first order differential equation we will need only one initial condition. For a second order, as we will see later on, we will need two conditions, but both are defined at the same point, and the point here at x equal to 0. So when I have something like this, I need to reformat it in that format. So dy by dx, I will keep it in one side, and then I will move this to this side. So this becomes 1.3 e to the minus of x minus 2y. Now this is your f of x and y. So before you do anything, before you start your solution, the first thing you have to do is to put the equation in this format. Now, once you are done with this format, then we will start to implement the algorithm of the solution, as we will see in the next page. This is a graphical representation of the solution, and we want to spend some time here try to understand what is going on here. So remember, this is an initial value problem, and we are identifying y at 0 equal to x0. Oh, sorry, this is y defined at 0 equal to x0. It's the value here. So we have here, which is y0. So we have here, this point is actually identified. This is given to us. This is the initial problem. You have an initial problem, like for example, y at 0 is equal to 2. So this is your y0, and this is your x0. So this is given to us. So this point is given to us. Now, this is the curve that represents actually the actual curve. This is the actual curve that we don't know. We don't draw. We don't know what is the solution. You know, we know that this is my independent variable, and this is the parameter that we are taking the derivative with respect to. So the solution will be a continuous function. Okay. So the solution is defined at different x's. Okay. So we want to find these values at different discrete points. So for example, I am interested to find what is the function y at, let's say, at 2 equal to what? The only thing I know is the differential equation and the initial value. This is the only thing I want. So I want to find y at 2. Okay. So then I have to move here. Now, as we know, what is dy by dx actually? dy by dx is nothing but the slope. So the function that you have here is equal to the slope. And what is the slope? The slope, as we know it, is the rise over the run. Is the difference in the y-axis to the x-axis. So I want to move from this point to this point. Okay. Now this point may not. I'm taking the tangent line using a step h. Step h will take us from x0 to x1. Okay, and now I know x0, y0. I know x1 because this is something I defined initially, that I will use a step of 0.5 or 1 or 0.05, whatever the step I'd like to take. So the only thing that is remaining is y1. Now we don't expect y1 to be the actual y1. This is the true value. So here, this is the error. There will be an error between what you estimate, this is the predicted value, and what is the true value. So how to find this y1? Okay, so the slope for this line is basically the differences in y's, y1 minus y0 divided by x1 minus x0. So this is your slope, and this is basically the function defined at x0, y0. Because remember, the function is equal to the slope. Okay, so this is always true. Now, this is my slope, which is equal to my function that is defined at x0 and y0. So now, if you look to this equation, actually, I will have here y1 minus y0 divided by x1 minus x0. This is equal to the function at x0, y0. Now, this is nothing but the dy by dx defined with this h. This is the h. So what is the unknown in this equation? We have only one unknown, which is y1. So if we solve for this, you will find that this is your y1. y1 is equal to y0 plus the function defined at the initial condition, which is given to us. This will be your, here, this is your x0, and this is your y0. The value is your y0. Okay, x0 is the variable that we have inside here. Okay, so what is this? This is your h. So I can now find y1 equal to y0 if x of 0 y0 times h. Now, what if I want to find that solution at y2 or y3 or y4? We keep doing this, and we use always the previous solution. Yeah, x0 is equal to 0, y0 is equal to 2. Okay, so sorry for the mix up. Okay, so this is the variable x, and this is the total value of the function at that specific x. Okay, so now I can generalize the solution having this equation that y at I plus 1, so the current or the current value of the function equal to the previous value of y times f defined at xi and yi, the previous value, times h, which is a constant. This is the same value that we will be having again and again. So the whole algorithm is actually summarized in this equation. Very simple, very easy to be implemented, and this is the main advantage of the error method. Now, we expect, especially if the function is changing abruptly, that the error will be really high, as we will see. So let's look to this equation. So here we have a linear initial value problem. This is, of course, we will be dealing. Linear. It's not really very important. It's linear or non-linear for us. We will not care much about it, but we'll deal mainly with linear functions. However, this is the thing that you have to look into. Do I have an initial value problem or a boundary value problem before you start solving your question? Because you will have in the exam an example for each. Could be an initial value problem or a boundary value problem. So this is something very crucial you have to look into. Now, we have the equation already given in the right format. I don't need to do anything Why? Because we have dy by dx in one side, and this is basically your fx of y. So it's done. I don't need to worry about it. And here is my initial condition. So this is my x0, and this is my y0. So as giving at 1, it doesn't have to be at 0, by the way. X0 is the initial value. Could be defined at any number. So it doesn't really matter which number it is. It doesn't mean that it has to be 0. Now, using the Euler method, so this is also something that you have to watch, because we will have 3 different techniques used in the initial value problem. So you have to know which technique we are talking about. Calculate the approximate value. Of course, this will be an approximate, not an exact value. Okay, exact value, then you have to go and solve this using the different methods, the analytical methods that you might have learned in differential equations solution. And you will not need to solve the equations using a closed form solution. If this is needed to you to find the actual error, then the answer will be given to you. Otherwise, you don't need to worry about it. We want to find the value at y at 1.5. So I know at 1, I want to go to 1.5. Okay, now the question is, what is the step size? The step size is given to us as 0.1 and 0.05. We want to see the impact of this. What is the impact if I reduce the step size from 0.1 to 0.05? So to go from y1 to y1.5, if I use the 0.1 step, first I have to find 1.1, then y1.2, y1.3, y1.4 until I reach to y1.5. So I have to go through all of this. And to find this, I will need the initial value, which is y of 1. Now to find this, I will need this value. Now this becomes the initial value. Then this value, and finally the 1.5. So in this approach, I will always need one value. And this is, if you recall, we talked about another classifications of initial value problems, that sometimes you need one value, sometimes you need multiple values, as we will see. Now also calculate the relative true error, knowing that this is the exact solution. Okay, so this is what we want to find. Okay, excellent. And it's very clear that if you take dy by dx, this will give you 2x e to the power of x squared minus 1. Okay, and this is equal to 2x. What is this? This is nothing but y, so this is 2x1. Okay, so as I said, you don't need to worry about it. You need just to know how to implement this in your solution. Okay, excellent. So let's move on now and see how to solve this problem. So h that we will have is equal to 0.1. That is the first thing that I am interested. Then I want to have my f of x of y, which is already given to me as 2xy. So this is also defined. So the solution y n plus 1 is equal to y of n plus h f of x of n y of n. So the existing solution is equal to the previous solution times h, which is given to me, and the function defined at the previous condition. As simple as that. It's very straightforward. So this y n plus 1, now let's go from the general formula to the specific formula, is equal to y n plus h. Now what is f x n y y n? This is equal to nothing but this, which is 2x of n y of n. Now this is the function. Okay. Now if I want to find y at 1.1, which is the n plus 1. Now my h is 0.1, so this is equal to the y at 1 plus h 2x, which is here, will be 1 times y of n, or y of 1 times y of 1. Okay. So this is equal to, what is y of 1? So this is equal to y of 1, which is 1, which is given to us as the initial condition. Y of 1 is 1. So this is 1 plus your h is 0.1 times 2 times 1 times 1. So this is give me 1.2. So h at 0.1 with h equal to 0.1, this is your y 1.1. What's next? I want to find y 1.2, which is equal to y at 1.1. Now this is my initial condition plus 0.1, doesn't change, 2 times the x, my x is 1.1 and my y is 1.2. This is your x and this is your y. Now my x is this is the value of x and this is the value of y. So this is equal to 1.464. So I will keep going until I reach to 1.5. Okay. Now if you look here, now this is x at 1.1. The true value, we know, as I said, we know the actual answer is given to us. So this is my true value, and I know that the approximation y 1.1 was equal to 1.2. Then we will find the error, what we found minus the actual value divided by 1.12. So this is 2.73%. Now, if you come and find the real error until you reached 1.5, as you will see here, the error is increasing. As we move from one step to another, you'll notice that the error is increasing, reaches 16.12%. And this is to understand this, why this is happening. If you look here, now once you reached here, you will go this way, you will go this way. If the function is going this way, you are going away actually from the answer. This is why for this solution, it's easy to implement. However, there is a huge error involved. Now let's see what will happen if I reduce h from 0.1 to 0.05. So my h now is equal to 0.005. Okay. So again, now I want to find y at 1.05, not 1.1, because my h is 0.05. So now this is my x. So this is equal to y at 1 plus the h, which is 0.05. Remember, the function is 2xy. This is my function. So it's 2 times the my x and times my y. So my x is the previous one, which is 1, and my y is 1. So this is equal to 1.1. Now let's find y at 1.1, which is the previous one, which is y at 1.05. Okay, plus 0.05 doesn't change, times 2 times, now the x is 1.05 and the y is equal to 1.1, which is your y at 1.05. And you find this is 1.2155, and we move on. Now when we reduce the steps, now how the error look like? Now if you go to until we reach the 1.5, the error is 9.08%. If you recall, the error in the previous one was equal to what? Was equal to 16%. So reducing the time step, and that sort of makes sense, help us to improve the accuracy, but in the same time will increase the number of iterations. Okay, so now the smaller the step you will take, you will find better solution, but you will have longer and longer number or needed number of iterations. Let's look to the second example, this one. So again, this is given to you. This is dy by dx. So this is your f of x and y given to you as x plus 1 minus 1 all square. And you are giving the initial condition. So this is your x 0 and this is your y 0. Using the Euler method, calculate the approximate value of y equal to 0.5. So we want to go from 0 to 0.5 at a rate of 0.1 step. So I will need to find 5 values. Y at 0.1, 0.2, 0.3, 0.4 until I reach to 0.5. I cannot jump to 0.5 directly. I have to go step by step until I reach my solution. Okay, so here my h is equal to 0.1. Okay, and my f of x and y is given to me as x plus y minus 1 squared. So my yn plus 1, same equation, y of n plus h, f of x of n, y of n. Okay, excellent. Now let me write the specific equation now, plus h, my f of x of n, y of n. This becomes equal to xn plus yn minus 1 all square. Now let's find y at 0.1, which is equal to y at 0 plus h, which is 0.1 times the function. Now what is x here? Start with x is equal to x0, which is 0, plus yn is 2 minus 1 all squared, and this is equal to 2.1. You go and find y at 0.2, which is equal to y at this is y at 0. This is y at 0.1 plus this doesn't change, stays the same, 0.1. Now I will use the most updated value for xn and yn. The xn is the 0.1. The x now is 0.1, the previous one, plus the y is from the previous one, again 2.1, and minus 1. This is a constant square, so this is equal to 2.244, and you keep until you reach y.5, which is equal to 3.2261. In this question, I didn't ask you for the error, so I didn't give you the exact answer. So it's either this or that. Either I will give you the actual answer, so I ask you to find the error, which is very simple, or I will give you, I will not give you this, I will not ask you for this, I will just ask you to do the calculations, and then you don't have to find the error, and just to find the value. Okay, now the second method that I'd like to talk to you about is the modified Euler method, which is called the Hume's formula. This is in literature, sometimes they call it improved, or sometimes they use Hume formula. Okay, so what is this formula? How it is done? Now this one we will use more than one value. So let's see here the formula. So first we will find something we call the predictor. The predictor is yn plus 1 star equal to yn plus h f of x of n, y of n. And if you look carefully, what is this? This is nothing but the Euler method. This is exactly the same formula that we use in the Euler method. It's the same one. But this is not the final value. We call this is the predictor. Now the corrector, we will come and find the yn plus 1, which is equal to y of n. Okay, this is the initial condition. H, same h. Now we will take the average of the function at x of n, y of n, which is the existing point, defining the slope, because we know that what is f of x y is basically dy by dx. So it's the slope of the function. So the slope of the function at the existing point and the slope of the function at the predictor, which is at xn plus 1, which is xn plus 1. We know it is nothing but x of n plus h, which we know. And at the predictor value or the Euler method value. Take the average of this. How this will give us a better answer? Let's look to this graphically and let's understand it. Okay, it looks a messy graph, but let's go step by step. So what we start with x is 0, y of 0. This is the starting point. Okay, and we want to move h. So we want to move from x0 to x of 1. So x0, x1 is given to us. Knowing h, I can find x of 1. Okay, so if this is your x of 0, then we defined the slope m, which is f of x of 0, y of 0. This is why this is how we derive this. This is derived from the slope. The slope defined at x of 0 and y of 0. So this is my slope. Now when I reach to this point of x1, this is my Euler method solution, or this is my predictor. So this is my predictor here, which is this solution. So this point is nothing but this solution, and this is, as we have seen that in the previous illustration, this is your nothing but this is your Euler method solution. So I am at this point. Now at this point, now I'd like to define another slope. At this point, we'll find another slope, which is this slope. The function defined at the new value now. So we will have this slope. This is the slope that we have. This is my new slope. Then what I will do, I have the previous slope and the new slope. I will take the average. This is the average of this slope, which is this one, which is this one. It's the average. And then this is the parallel line. I will move this until it intersects this parallel. When you take something in parallel, you are not changing actually your slope, but you are changing your x. I want to go back to x0 because I want to start from x0. So I will take this back to x0, back to the original point, but now instead of having this solid line curve, this will be my curve, and this will be my solution. And you see, this is the new correct answer, which is much closer to the actual value, which is here. Okay, so this let's have an example, and with this I will end of my today's lecture. So what I will do, I will solve the same problem that we did before. This is just the same problem we did before, but now instead of using the Euler method, I will use the modified Euler method, and I will use x equal to 0.1 and h equal to 0.05, and we want to find the relative true error as we did in the previous one. Okay, so we will have here h equal to 0.1. Okay. Now, with the function is defined to us already, which is equal to the dy by dx is equal to 2xy, the same function we had before. So we start with the predictor, x star at n plus 1, which is the Euler formula, which is yn plus h times f of x of n, y of n, which is equal to y of n plus h times 2x of n, y of n, which is this function. Okay, so now I will find the predictor at 1.1, which is equal to y at 1 plus 0.1 times 2 times 1 times 1, which is equal to 1.2. And if you remember, this was the y 1.1 using the Euler method. So nothing yet changed. So this is exactly the same thing. Now here is the modification. Now I need to find y at n plus 1. Now this is the modified one, which will be yn plus h f of x of n y of n plus f of x of n plus 1. So now I'm using, if you recall, in the predictor, we always use the previous values. Now I'm using the previous value and the existing value. So I need 2 points to be able to find the answer, or the approximate answer. And yn plus 1 star divided by 2. So I'm taking the average of these two slopes. So let me be more specific here. I want to find y 1.1. So this is equal to y1, okay, plus equal to, this is my initial condition, h is 0.1, nothing changed so far. Now I need to find my f of x of n y of n. So this will be equal to 2 times x of n y of n. So it's 2 times 1 times 1. Okay, so this is because this is nothing but 2 x of n y of n. And this is 2 x of n plus 1 y star n plus 1, because this is the function now. So this becomes 2 my x of n, which is x of, it is 1. X of n is 1, my initial value, and the value defined at 1, so it's 2 times 1 times 1, plus 2 times x of n plus 1, which is the same. So this will be 1 point. So there will be 2 times 1.1 times the function, the star function defined at 1.1, which is 1.2. I just found this, defined by, or divided by 2. So if this is equal to 1.232. And we move on. So now if you see, this is the solution now with the error here. See, the error is 1.13. I did not change the number of steps, but at the same time, the error was more than 16%, and now it's dropped to 1.13%. Okay, so you can see here is a huge improvement using the modified by just adding a corrector to the Euler method. I'm actually correcting the Euler method by having the other extra term, so that we will be able to